So in the computer world, it's basically the same idea, arranging items in a specific order. The source uses this really nice visual. Imagine a mixed-up pile of colored dots. Reds, yellows, blues, all messy. A sorting algorithm is like the smart process that takes that mess and lines them up neatly. All the yellows here, then the reds, then the blues,
Exactly. Bringing order from chaos. And it's fundamental because computers deal with so much data. Having it sorted makes lots of other tasks way, way faster.
And there's not just one way to do it, apparently.
Oh, definitely not. That's what's fascinating. The source mentions bubble sort, merge sort, quick sort, heap sort. Each one is a different strategy.
Different approaches to get the same neat pile of dots?
Pretty much. Bubble sort is like easy to grasp, but often super slow, especially for big lists. It has this, they call it quadratic complexity, meaning if your list doubles, the sorting type, like quadruples, it gets bad fast.
Yikes.
Yeah. Whereas quicksort or merge sort, much, much smarter. They're closer to nearly linear. They can chew through millions, even billions of items way more efficiently. It's all about handling scale. That efficiency difference is huge in practice.
That makes a huge difference, yeah. Okay, so you've sorted your massive pile of digital dots. Now, how do you find one specific dot or one specific piece of information?
Right. That's the next logical step, searching. How do you locate something specific in a collection, whether it's sorted or not?
The document gives a number example, right? Like an array, 13, 9, 21, 15, 39, 19, 27. If you need to find 39, the searching algorithm is just the instructions for how the computer looks for it.
And again, how you look matters a lot, especially for speed. The source points out linear search first.
That sounds straightforward. Just check everything one by one.
Yep. Simple, but potentially slow. If 39 is the last number in a million-item list, you check a million things.
Oof, okay, not ideal.
Not for big data sets, no. That's where binary search comes in, if the data's already sorted. Ah, so sorting helps searching, too.
Massively. Binary search keeps cutting the search area in half. Remember that million-item list?
Yeah.
Linear search might take a million steps. Binary search, maybe 20.
20? Wow. Okay, that's a difference.
Huge difference. It's why sorted data is so valuable. And then there's BFS and DFS, breadth first search and depth first search.
Right, those sound more complex.
They're more for exploring connections, like in a network. Think finding the shortest path in a map or exploring all your connections on a social network. Different ways to navigate complex structures.
Gotcha. So moving from just organizing and finding, sometimes the problem itself is just huge, right? Like really complex. How do computers even start?
Yeah, that's where we get into more powerful techniques. And the first one is, well, it's a bit mind-bending sometimes.
Or
recursion.
Recursion. Okay. Heard of it, seems recursive.
Exactly. It's a technique where the solution to a problem depends on solutions to smaller versions of the same problem.
The source uses analogies like tree branches. Each smaller branch looks kind of like the bigger one it came from. Or in code, it's a function that actually calls itself.
Whoa. Okay, a function calling itself. How does that work in practice?
Well, the factorial example in the source is perfect. To calculate 5 factorial, written as 5, you need 5 times 4 factorial.
Okay.
But to get 4 factorial, you need 4 times 3 factorial. And you keep going, breaking it down. 3 times 2 factorial.
Which is 2 times 1 factorial.
Exactly. And 1 factorial is just 1. That's the base case, the point where it stops breaking down. Then the answers build back up. 2 times 1 is 2, then 3 times 2 is 6, 4 times 6 is 24, and finally 5 times 24 is 120.
Ah, I see. So you break it down until it's simple, solve the simple bit, then combine back up.
Precisely. It's really elegant for problems that have that self-similar structure.
So this idea of breaking things down, that sounds like a strategy in itself.
It absolutely is. It leads directly to a really important paradigm called divide and conquer.
Divide and conquer. Makes sense. You take a big problem.
And you break it. You divide it into smaller, more manageable subproblems. Ideally ones that are similar to the original, just smaller.
Like we saw with recursion.
Often, yeah. Recursion is frequently used in the conquer step. So the source lays out 3 steps. First, divide the problem. Second, conquer the subproblems, often recursively until they're easy.
Okay.
And third, combine the solutions from the subproblems to get the final answer for the big original problem. Merge sort, which we mentioned earlier. Classic divide and conquer.
That's a really powerful mental model for tackling complexity. Break it down, solve the bits, put it back together.
Exactly. Super useful.
Right, let's shift gears a bit. Let's talk about managing all this data efficiently, especially getting to it quickly. Hashing algorithms.
Hashing. Yeah, you use this constantly without even realizing it. Logging into websites, that's hashing protecting your password.
So my password isn't just stored as plain text.
Definitely not, or it shouldn't be. Hashing turns your password or any data into a unique fixed-size string of characters, the hash. It uses a special hash function. Think of it like creating a unique ID or fingerprint for the data.
And this helps find things fast.
Incredibly fast. Imagine a huge database. Instead of searching through everything, the system calculates the hash of what you're looking for and can often jump almost directly to the right spot in storage using that hash value. It's stored in something called a hash table.
Like an index.
A very smart index, yeah. The source shows this flow. Plain text goes in, goes through the hashing algorithm, and out comes this unique hashed text.
And you mentioned security and integrity.
Right, because even a tiny change to the original data, like changing one letter in your password or one bit in a file, results in a completely different hash.
So you can tell if something's been tampered with just by comparing the hash.
Exactly. If the hash doesn't match the stored one, something's wrong. There are challenges, like collisions, where two different inputs might accidentally produce the same hash, but good algorithms minimize that.
Wow. Okay. That's clever. And it brings us to our last one, which sounds related to recursion, dynamic programming.
It is. It builds on recursion. Dynamic programming sounds fancy, but the source nails the simple explanation. It's basically recursion with memoization.
Memoization, like making memos.
Sort of. It means remembering. It's about storing the results of calculations you've already done, specifically for those subproblems in recursion.
Why would you need to do that?
Because sometimes when you break a big problem down recursively, you end up solving the exact same smaller subproblem multiple times in different parts of the calculation.
Redundant work.
Exactly. Wasted effort. Think of that factorial example. If calculating, say, 10 factorial involves somehow needing 5 factorial multiple times down different paths, why recalculate it each time?
You just want to look up the answer you got the first time.
Precisely. That's memoization. Dynamic programming systematically calculates the results for subproblems once, stores them in a memo, often just an array or table, and then just retrieves the stored answer whenever that subproblem pops up again.
So it makes recursion much more efficient for certain types of problems.
Dramatically more efficient, especially for problems with lots of these overlapping subproblems. It can turn something that would take like an impossibly long time into something manageable. It's about avoiding that repeated work.
Okay, that's a really smart optimization. So looking back, we've covered quite a journey here.
We really have.
From basic essential stuff like sorting and searching to more advanced ways of thinking like recursion and divide and conquer. And then these clever techniques like hashing for speed and integrity and dynamic programming to optimize those recursive solutions.
Yeah, they're not just abstract ideas. These are the tools, the logical blueprints that make so much of our modern tech possible.
From organizing your photos to, I guess, complex AI making decisions.
Absolutely. It's all built on these foundational ways of telling computers how to solve problems efficiently and reliably. It's the logic underpinning our digital lives.
So maybe a final thought for everyone listening. Next time you're using your phone, searching online, or even just, I don't know, organizing your own thoughts for a project. Take a second to think about these hidden algorithms working away. Sorting, searching, maybe even doing something like dynamic programming without you seeing it. And maybe ask yourself, how could understanding these core ideas like breaking problems down or finding efficient ways to search or remembering past solutions, how could that change how you solve problems? Not just tech problems, but everyday challenges.
Yeah. Could you design a new algorithm for your morning routine? Or for how you plan a big trip?
Exactly. What efficiencies could you find in your own life? Something to think about. Until next time, keep diving deep.